say good afternoon. This presentation, I will exploit part of the presentation of the previous speaker because in some parts we overlapped a little bit. And I already want to tell you that I won't enter into the technical details of pump hydro. It's not the place. I would like just to give you an overview of the possible solution and why it would be useful to hybridize even this technology and what are the benefits of doing this. So let's start from the very beginning. So what is pump hydro? The precedent speaker already showed you, so you have already an idea. It's like a hydropower plant, but you have another function, which is the possibility of pumping back the water from the bottom to the top of this scheme in order to use water as a green battery. So you can store water and you can use it when it's time and when you think it's useful and maybe also economically valuable for you to use it. Here you can see that there are some general performance of the technology. The cycle efficiency is around 80%, 85%. And the discharge time can be extremely wide. You can go from 8 hours up to one entire season. So hydropower is really a seasonal storage system that can cover quite a long period if the reservoir, the upper reservoir, is big enough. It's also a well-spread technology. Here you can see the amount of power plants installed at global level. As you can see, there are 3 main points of concentration in the US, in Europe, and in China. China is running a lot, so they are building in this very moment a lot of pumped hydropower plants. So they are covering the gap quite rapidly. And I would like just to give you a brief overview of the possible configuration that you can find. Thor, before me, just mentioned this possibility of having an open loop and a closed loop configuration. The main difference is that in the open loop configuration, the upper reservoir is characterized by the possibility of having natural inflows, varying the water availability during 1 year of operation, depending on the rains, depending on the snow melting, depending on several factors. Whereas in the closed loop configuration, you have the same amount of water, we could say, but it is moved from the upper reservoir to the lower reservoir and back. This is a sort of limit because you do not exploit the possibility of having natural inflows, but it also opens the possibility of exploiting more sites for building a pumped hydropower plant. And moreover, just to mention, a new research on this topic is to change the fluid used in the pumped hydro configuration, because there is one startup in UK working on the possibility of using a high-density fluid instead of water in order to exploit the factor that was mentioned in the formula before. The density is one of the factors contributing to the power. So if you are able to increase the density of the fluid that you are pumping forth and back, you can increase the amount of power and the energy that you are storing. Of course, this can be done only with the closed loop because you cannot use river for this kind of experiments. But it's extremely difficult to find a proper fluid. This startup is working on a fluid composed of water and solid particles. But there are several challenges because you have to avoid the deposition, you have to avoid the wear and tear, the increase of wear and tear in the machine. So it's extremely complex. We are speaking about a very low maturity level of this kind of solutions. But this was just to mention to you this possibility. Looking at the more standard configuration of pump hydro, there are possible layouts. The classification is mainly based on the number of machines that are installed in the configuration. You have two main types of machine in a pump hydro. The hydraulic machine, converting the hydraulic energy of water into mechanical energy, and then the electrical machine, converting mechanical energy into electricity. So this configuration depends on the number of these machines installed in the plant. And the main difference and the choice between the different configuration is based on two main factors: the performance that you can achieve, so efficiency, operating range, in some cases wear and tear. In other cases, there are also other aspects to consider, but these are the main two. And then cost, because as Peter mentioned this morning, you have always to consider that a plant owner looks at tangible values to decide the final choice, design choice in the power plant. So if we take into account these two main factors, there are three possible configurations that you can find. This is the most standard one, the quaternary configuration. Quaternary means 4, and there are indeed 2 hydraulic machines and 2 electric machines. And you can see these machines in this simple scheme. Here you can see one hydraulic machine, the pump, pumping the water from the lower reservoir to the upper reservoir, and to work, the pump needs a motor, an electric motor. So here you have one hydraulic machine and one electric machine, and on the other side you have a standard hydropower plant with a turbine, hydraulic machine, plus a generator, an electric machine. So in total you have 4 different machines installed in this configuration. And this is extremely interesting for an engineer because you can optimize everything. And if you optimize everything, the design and the management, you can reach very high efficiency in both operating mode, both in generation and in pumping mode. So this configuration is characterized by very high efficiency and also very high flexibility. This means that you can use different flow rate, volumetric flow rates, different head, and you can operate with your power plant in a wide range of operating conditions. So these are 2 extremely interesting performance aspects to consider when you have to decide the configuration of your power plant. But there is one drawback, the cost, because you have to consider that in a power plant, the equipment, the electromechanical equipment has a big weight on the total cost of the power plant. In small hydropower plant, the cost of the electromechanical equipment can reach up to 40–50% of the entire cost of the power plant. So it's really a big share. And this is a factor that has to be considered if you want to use this kind of configuration. The other configuration is the ternary one. So you can see very simple. Ternary means 3. So we are losing one machine. And in this case, we are losing one electric machine. Because as you can see in this scheme, there is a pump. This one is a pump. The other on the top is in light blue is a turbine, and they are connected on the same shaft, so they are working together. And there is just one electric machine working in both modes. So you have one electric machine that can work as a motor for the pump or as a generator for the turbine. These have some advantages and some drawbacks. The advantage is that you still have 2 hydraulic machines, and you have to consider that the efficiency of the hydraulic machine is extremely, affects a lot the global efficiency of the plant. So if you can design specifically the pump and the turbine for a power plant, you can reach very high efficiency. Like it was mentioned before, state-of-the-art hydraulic turbine can reach up to 95% of efficiency without any problems. So this is one good point, one advantage of this configuration. Another advantage is operational. The rotation direction of the shaft. I will try to explain. You have to imagine that your power plant is working as a standard hydropower plant. So you are producing electricity. This means that your turbine up there is working and it's rotating and producing mechanical energy and then electricity. And then at some point you decide that it's better not to produce, but maybe to consume electricity. So you have to change your operating mode from turbine to pumping. And what does it happen? Do I have to stop the turbine and to start up again with the pump or not? If you have this kind of configuration, you do not have to do anything. The shaft rotates in the same direction, so you do not have to stop the turbine. You have just to attach the pump to the shaft, and the pump starts to operate. And at the very end, the turbine is only driven by the rotation of the pump, and the pump with the motor revert the direction of the water and starts to pump back from the lower reservoir to the upper reservoir. This change in operation mode is quite rapid, is quite fast. And this is good because we have seen that reaction time is one of the KPI of a storage technology. So this is definitely one important factor. So the change in operation mode is extremely rapid. Summarizing the benefits of this configuration, the efficiency is still quite high. Not as high as for the quaternary configuration, but still high. And the flexibility also is still high. But the costs are a little bit less than before, because you have eliminated one electric machine. So you have to buy only 3 machines, not 4. And this is an economic advantage. The last but not the least configuration is the binary configuration. You can see the thought that has driven the innovation in this field. The idea is to reduce the number of machines because you have to spend less money. So they try to reduce with one configuration by one the number of machines. And in this configuration, they were able to achieve the pump hydropower operation only with 2 machines, 1 turbine and 1 electric machine. So you have down here this hydraulic machine that is called a reversible pump turbine. It means that it could work both as a pump and as a turbine. But you have to reverse the rotation direction. So if it has to pump, it rotates in one direction. If you want to start generating, you have to stop the machine and rotates in the other direction. And the electric machine follows you. So if you are pumping, it works as a motor. If you are generating, it works as a generator. So it is an extremely compact solution, but there are several drawbacks because the design of the hydraulic machine is a compromise. You cannot optimize the pumping mode because otherwise the efficiency in generating mode is too low, and you can't do the opposite. So you have to find a compromise, and this comes at a price. The machine is not so much flexible, and the efficiency is not so high as in the previous cases. Moreover, as I said, you have to change the rotation direction if you want to change the operating mode, and this requires time. How much? We can say 10 years ago, the time for reversing the operating mode was around a couple of minutes. Because you have seen it is not only a matter of stopping the turbine and reversing the rotation direction. This can be done in seconds. But there are mass of water connected to the turbine. So you have to consider, or the dynamic of the system, you have to avoid the pipes to explode. So you need to be extremely careful. And to do this reverse of operating modes, 10 years ago were necessary at least 3-4 minutes, which seems to be a small period of time, but in some cases it's like hundreds of years of delay. Whereas now this time has been slightly reduced and we are in the order of 1 minute, 1 minute and a half, which is still quite high. I mean, from 100% generation to 100% pumping and the opposite. If you are just changing a little bit the operating mode from 0 to 30 is much faster. So what are the drawbacks and the benefits? It's quite intuitive. The efficiency is lower, the flexibility is lower, we could say medium, but the costs are extremely lower than the previous configuration. And this is why this solution is one of the most spread at the time being, because it's less expensive. It requires a small powerhouse because the machines are smaller. They are only 2 instead of 4. This means also less civil works to build the powerhouse. You have to consider that generally the powerhouse are in cavern, so you have also to do underground works, and this cost a lot. So in the last years, this configuration has been preferred in comparison with the other. Moreover, they have tried, since this configuration was so interesting from the point of view, from the economical point of view, they have tried to introduce some innovation in order to improve the performance of this configuration. In this case, I would like just to show you a video because this solution is quite complex. But in this video of one hydraulic turbine manufacturer, it's easily understood, explained. Let me.
2 reservoirs located at 2 different elevations. They're linked by conduits.
No.
And the plant is generally underground.
There is background noise, so I will explain to you. As you can see here, this is a standard. Okay, if you can solve it.
Electricity is needed. The
Okay.
gates are open and the water flows through, driving the turbines, which generate electricity.
Wait, here maybe.
Did you turn off the sound of your own computer?
It is.
No, it's not the microphone, it's loudspeaker.
Okay, but if I do like that, you cannot hear.
You don't need your loudspeaker.
Doesn't work like that.
Oh, no, because then I can't hear. Oh.
Let me show if I can do in another way.
No. If I mute this one.
Okay.
Oh, yeah. I don't dare to touch anything.
Anyway, I will like just to, I will try to explain to you. You can see the video. It's slow motion. Let me try one thing, and then if it is not possible, I will. No, okay. So the idea of the variable speed technology. without the sound, it's easier if I explain to you with my own words. The idea of the variable speed technology is to enable the possibility of varying the rotation rate of the shaft, so of the machine, because generally in this configuration the machine are rotating at a fixed rotation rate, which is needed to be synchronized with the grid. But this rotation rate has an influence also on the power that the power plant can produce or can consume from the grid. If you're able to change the rotation rate, it's like tuning the power of the system. So increasing and decreasing the rotation rate means increasing and decreasing the power consumption and the power generation of the power plant. And this is extremely useful because adding one component, the frequency converter, that means power electronics to the system, you can enable this function of varying the rotation speed of the power plant, and binary configuration becomes extremely flexible in comparison with the standard configuration with fixed rotation rate. So this was a pretty huge innovation in the field. It's already a state-of-the-art innovation because the last power plant, as the one shown before, Nandedrans and also Goldstahl, they both have the variable speed technology installed. And they enable the possibility of increasing the flexibility of the binary configuration. Why they put so much effort in binary configuration instead of going to ternary or quaternary configuration, which are much more efficient and flexible? Because of the economic advantages that comes with the binary configuration. And the proof of what I'm saying is in this graph. In this graph, you can see the installed power on the x-axis and the difference in level between the two reservoirs on the y-axis. And as you can see, the great part of the configuration belongs to the ternary and binary groups. So the quaternary is a whole configuration that has been abandoned during the last 50 years, and they are much more focusing on these two configurations. And the binary configuration is used always when it is possible. It is not possible above 800 meters because it is not possible to have one reversible machine working well in all the possible operating conditions. So it is not technically feasible to have the binary configuration in this area. So this area is covered only by ternary configuration. So this was just a brief introduction to give you an overview of the technology and pumped hydropower plant. But I would like to just discuss with you about the possible role of pumped hydropower or storage more in general in the future grid. And let's start with the question, what kind of energy storage solution we need in the future grid? We have seen several examples already this morning and in the previous presentation. So you are well aware that there are batteries, supercapacitors, thermal storage, pumped hydro, and a lot of other storage technologies. They can be classified in different ways. One way of classifying the storage solution is on the reaction time. So here in this figure, you can see the time of reaction. One is 1 second, 15 seconds, 60 seconds, hour. So there is energy storage. Energy storage is this one. And you can speak of energy storage if you are referring to a storage capacity extremely large, seasonal, monthly, weekly storage capacity. Then you have power storage when the storage capacity is limited, but extremely fast in reacting. And this area is the very fast storage technologies, the technology that are capable of reacting in less than 1 second, in milliseconds, but maybe they are a little bit limited in storage capacity. They cannot do this job for hours. They can do this job only for minutes. Why we need also this section of storage system? We are well aware that we need long-term storage. I think you also know why we need a fast storage system, because we need those for the grid stability. How many of you are quite aware of the challenge of the stability of frequency regulation services? Can you raise your hand? Okay, half of the audience. So I will give a brief overview, very simplified. So for technical people, excuse me, it's extremely simplified just to give the main concept and ideas. The electrical grid needs to be stable. And what does stable mean? It means that the energy generated and injected into the grid should be equal second by second, millisecond by millisecond to the energy consumed in the grid. So if at a certain instant there is a sudden increase in loads, a washing machine, maybe this is not a big example, but just to make you understand, if someone is turning on a washing machine and there is a small increase in consumption, this is not even seen in the grid, but let's assume it is relevant. This balance is lost, and you have to recover it as soon as possible. So once this happens, you need to increase immediately the power production and the energy generation. So you have to rely on renewable power plants, on pumped hydropower plants, or on fossil fuel power plants to restore the balance. Otherwise, what happens? Blackouts, like we have seen in Spain and in Portugal recently. The reason of the blackout are not so clear, but the things that is clear at this balance got lost. And at the very end, the grid collapsed. So, from a technical point of view, if there is a mismatch between energy generation and energy consumption, the frequency of a grid changes. You should know that when you plug your device in the grid to get the electricity is flowing in the grid with a certain frequency. In Europe is 50 hertz. Whereas in other countries like South America, it could be also 60 hertz, but let's focus on 50 hertz. If there is a mismatch between electricity generation and electricity consumption, the frequency of the electrical grid changes. For example, in the previous slides, we have seen an increase of the loads. If there are extra loads, the frequency of the system reduces. And it goes down to 49.5, 49.2. And this variation in frequency cannot be sustained by the grid for a long time. Because if my power plant is connected to the grid, is synchronized to the grid, and my willingness for the safety of my power plant, it is to have a grid at 50 hertz. If something happens and the frequency of the system changes, I'm forced to disconnect my power plant for the own safety of the power plant. It's mandatory. So if this variation is not recovered extremely rapidly, the result is the blackout, because all the system get disconnected, and at a certain point you have no electrical generation and no electricity for the loads. So you have a blackout. To react to this situation, you need the technologies. And this is one of the direction in which all the researchers working in this field are trying to go, to react also to sudden event in order to avoid blackouts. And this is the real capacity of pumped hydropower plant in terms of reaction time. As you can see from the past, they have tried to reduce with different solution, ternary and variable speed solution, in order to reduce the reaction time of pumped hydropower plant. Why they are doing this? Because one point could be, and one comment from you could be, pumped hydro is a seasonal storage. So it's a long-term storage system. Why they are trying to make it fast? What's the need? The need is the market. At the time being, the main revenues are here, so they are pushing in this direction in order to try to gain money. And pumped hydro is not capable of going in this direction. This is the very last limit. We are not able to go in that direction. So if we look again at this graph, pumped hydro can cover without any problem this section. There are some problems in this section because the mechanical stress is extremely relevant. And we have life reduction and wear and tear, so extraordinary maintenance required. The very last part is impossible. Maybe power plant owner will tell you that it is possible, but it is not. The reality is this one. It is not. So the only solution is to hybridize. The only solution is to go for an hybrid solution. And the most boosted solution in this moment is to hybridize pumped hydro with batteries or with flywheels. And here you can see an example of pumped hydro hybridized with batteries. I will try to give you an overview. If you hybridize these two technologies, you will have a virtual power plant. And this virtual power plant will enable the possibility of covering all the needs. So you will have on one side pumped hydro with its seasonal storage capacity, energy shifting, peak saving, and so on. And the fast storage will enable the possibility of earning money from the frequency regulation services. So to do this, how does it work, this kind of hybrid power plants? You have, for example, a frequency drop, like in this case, you can see, this is a real event. The frequency dropped from 50 Hertz down. So you need to react to avoid the blackout. You need to have an extra generation, so you need to increase the power production. Pumped hydro can do it, but is extremely painful from an economical point of view, life reduction and wear and tear. So the best is to exploit the battery, to do the first reaction, the very rapid one, and then to use pumped hydro to inject the great power ramp up in a slower motion. So you can plan your system in order to have a fast reaction from the batteries, and then great power capacity from the pumped hydro power plant. Here is how you can split the work between the different technologies, but I will not enter into this detail. I would like just to show you that there is a way to measure the impact of this behavior on the technology, wear and tear, both of the battery, of pumped hydro, optimal size, optimal control logic, and everything. I would like just to, these are the KPIs that I would like to show, but I'm running out of time, so I will cut this. This is to show that this is feasible, but I would like to go to the real example to conclude. Okay. This was the first pilot built in Europe. It was built within a European project called the X-Flex Hydro. And one of the units in this Vogelgrün power plant was hybridized with a battery system of less than 1 megawatt. And they were able to demonstrate in this pilot that it makes sense because there is an increase in reaction time of the plant, increasing contribution to the grid stability, and a reduction of the mechanical stress of pump hydro. But these are not the only benefits that you can have if you hybridize the technologies. You can do more. And we are doing more in this direction because there is another example that I would like to show you. This is Innovation Fund, a project founded within the Innovation Fund. It's called Best for Hydro. And it's a real power plant, not a pilot. This is a real power plant in which the hydropower plant of Dossi, 40 megawatts, is going to be hybridized with a battery system of 4 megawatts. The plant is from Enel in Italy. They are working on the implementation of the BESS system, the integration of the BESS system. We are collaborating with them in doing this. And the benefits that we expect to have from the entry in operation are relevant because we are expecting to reduce the CO2 emission. How? By increasing by providing grid regulation services, so by substituting fossil fuels in doing this, but also increasing the plant efficiency we were discussing this morning. The BESS can help the power plant, the hydropower plant, to operate better at higher efficiency. And this also will increase the plant production. We are expecting a plus 5% of increase in plant production thanks to the hybridization. So this is really a multi-scale hybridization solution, and this is the direction in which we are going, at least regarding pump hydro. And this is all.